All right. So, in chapter 18, our first chapter this semester, we learned about essentially two things: charge and field. Well, we also learned about force, but force and field are very similar. But we learned about some of the properties of charge, that they exert forces on each other, attractive, repulsive forces. And then we learned about Coulomb's law, which helps us calculate those forces. And then we decided, well, what if we just wanted to know what force you would feel if you did put a charge in there? And that's what we called the electric field. So we burned through that pretty quickly. But it turns out that measuring electric field is a little bit difficult. And measuring charge is even more difficult. But there is something that we can measure that's not very difficult to measure, and it's related to both charge and field. And that is electric potential energy. And what this means is, if I put a charge in an electric field, it will be accelerated. It will move one way or the other, depending on what kind of charge it is and which way the field is pointing. It will accelerate depending on how strong the field is and how big the charge is, what mass is, and how much charge there is. But it will move in some way and will gain some energy because of that acceleration, because it will change its velocity. And that gain in energy, and it can actually gain energy, or you could think of it as losing energy if it's a negative charge. It's also a way to think of it, because the potential energy that it can gain will be positive or negative depending on where we choose our zero potential to be, because just like gravitational potential energy, an electric potential energy depends on where you choose your zero. You have to choose the 0 point, or the ground level, you might think of it as. But we need to figure out what this means mathematically. What does it mean to have a potential energy electrically? When it was gravity, how did we change the potential energy of something in a gravitational field?
Set it higher up.
That's right. We either lifted it up, or we moved it down, right? Or we let it fall, or we shot it upward, right? We changed its height, because at different heights, the Earth has a different ability to accelerate an object. If it's higher above the ground, it can accelerate the object for longer before it hits the ground, right? And we don't necessarily have to use the ground as our 0 point. We can also use other places. The top of a cliff can be the 0 point, and the bottom of the cliff can be a negative potential energy, right? So with gravitational potential energy, it depended on the height. The higher you were above your 0 point, whatever you called that, or the lower you were according to that 0 point, it either gave you more potential energy or less potential energy, and you could have positive and negative potential energy. In electric fields, we have a little more complexity, because we're not just moving a mass up and down, we're actually going to move a charge, and that charge could be positive or negative, back and forth. And if the charge is positive, moving it one way will have one effect on its potential energy. And if it's negative and you move it the same way, it'll have the opposite effect, because it's a negative charge. So that gets a little bit confusing to talk about electric potential energy because of the positive-negative charge thing. So we do something very similar that we did to electric field. Remember, we took electric force and we removed one of the distance things, and we removed one of the charge things. Well, we didn't remove one of the distance things, sorry. We just removed one of the charges from the equation, so that we were only looking at the charge that was creating the field we were interested in. Remember that? So the electric field only cares about one charge. It cares about the charge making the field. And then we used a test charge to figure out what the field was, and that test charge was positive. We're going to do the same thing with potential energy. Instead of talking about the potential energy of positive charges or the potential energy of negative charges, we're only going to talk about potential. We're going to not call it potential energy anymore, we're going to call it potential. And we're only going to use a positive test charge to calculate this value. So we're going to do the same thing we did with electric field. We're going to drop out one of the charges and only talk about the potential if it was a positive charge. And then if ends up being a negative charge, we'll just realize that that's going to be opposite. Because it gets too confusing to have two sets of equations. One set of equations for negative charges, one for positive charges. So how are we going to define this potential energy and this potential eventually with electric fields? Let's start with a very simple situation, which is what we do a lot in physics. We're going to create an electric field that is pretty uniform by making this is what we call a parallel plate capacitor, where we have a wall of positive charge over here and a wall of negative charge over here. So the field lines are going to start on the positive charges and go to the right towards the negative charges. And then we're going to put a positive test charge inside this thing and decide what its potential energy is. Now remember that from our previous semester, potential energy and kinetic energy are on either side of an equation. The change in potential energy will equal the change in kinetic energy if you put them on either side of this equation. As long as there's no outside work being done, no friction or anything else taking energy out of the system or whatever, or anything on the outside putting energy into the system, then this equation is the conservation of energy equation. And that works both for gravity and electricity, it turns out. So what that equation means is that if our kinetic energy is big, our potential energy has to be small, right? And if our kinetic energy is small, our potential energy has to be big. That's what that equation essentially means. So, if I release this charge right here, close to this positive plate, where is my kinetic energy going to be biggest? If we let it go and see what happens, at one point in space between these two plates, will the kinetic energy of that positive charge be the biggest in this electric field? Yeah, when it's close to that plate at point B, right? When it gets close to that plate at point B, there's a little hole in the plates that's allowed to shoot out. This turns out to be an accelerator that accelerates positive charges right out of this thing, right? And once it gets close to that point at point B, it will leave the electric field and it won't be accelerated anymore, but it will be going as fast as it can be going. So when that positive charge Q is close to point B, its kinetic energy is biggest and its potential energy is smallest, right? And it's just the opposite at point A. At point A, its potential energy is the greatest, and it's because it has this potential to accelerate, it just hasn't done it. What happens if I move it closer to the positively charged plate? Does its potential energy increase or decrease? It increases, right? Because the pushing from the positive plate becomes more and more and more and more. And its potential to accelerate becomes more and more and more. Right? So this is how we're going to define potential energy for charges. Is this ability for it to accelerate, right? Or at the low end of potential energy, it's going to be at its maximum kinetic energy. You could think of that. It's the same for the ball on the hill. If the ball is at the top of the hill, it has its maximum potential. And if it's at the bottom of the hill, it has its minimum potential, and vice versa for the kinetic energy, right? Now, it still matters where we call this, it still matters where we choose our zero, but it doesn't change where the high and the low is. That's something that can be confusing. The high and the low will be at the same place no matter where we choose our zero. It's just going to be positives or negatives and positives or whatever. But it will still be high, low. High positive charges will feel high potentials when they're closer and closer to a source of field that is positive charge field, positive charge source of field, and they will be lower and lower and lower as they get further away from it. Negative charges, of course, will have the opposite kind of potential energy, but like I said, we don't really want to get into that too much. What we want to do is we want to define a new value that gives us, that removes the charge that's feeling this energy, removes that charge from the equation. So what we're going to do is we're going to say the potential energy divided by the Q that is feeling that energy, or has that energy, is going to equal a new value that we're going to call the potential, and sometimes it's called the voltage. You've heard that before. So the potential or the voltage. And instead of talking about the potential as if it's some absolute thing, it's not an absolute thing. It's like potential energy is not absolute. It depends on where you choose your zero. So instead of talking about the potential just as the potential, we're going to always talk about the potential as a difference between two potentials. So we're going to have one potential here, one potential here. The zero is wherever we chose it, but the difference between those potentials is going to tell us something important. The difference between those two potentials is going to tell us what kind of energy this particle can gain or can lose if it goes from one point to another point. So the electric potential is defined as the potential energy per unit charge. You could think of it as. And here is that definition of the change in potential between 2 points, point B and point A, which might have different field strengths, might have the same field strength, whatever else, but that would be equal to the change in potential energy over Q. And it turns out that the units for this are in joules per coulomb, energy per charge, and we call that the volt, named after Alejandro Volta from Spain. Now, how do we put some numbers to this? Here we have an example with a 12-volt motorcycle battery. So what does that tell us? If a motorcycle battery has 12 volts of voltage or 12 volts of potential difference, we'll call that, then, and you have 2 points on the battery. You have the positive and the negative post, right? So what does that tell us if it's a 12-volt battery? Potential difference. What are volts? They're joules per coulomb, right? That means if you have a charge that goes from one of those posts to the other post, they will experience a change in potential energy per charge of 12 joules per coulomb, right? So if it was 1 coulomb of charge going from one post to the other, then they would experience 12 joules of energy change. It might be an increase in potential energy, it might be an increase in kinetic energy, it might be a decrease in either. But they will, if a charge of 1 coulomb goes from one post to the other through the battery or through a circuit connected to the battery, they will experience that change in energy. That's what it means. 12 joules. How much is 12 joules? Well, joules are Newton meters, right? So if you have 1 Newton that falls 1 meter, what is 1 Newton? 1 Newton is something that weighs about 10 newtons weighs about 2 pounds. So 1 Newton weighs about 0.2 pounds. That's not very much, but 12 newtons is about 2 pounds, 2 or 3 pounds. So you get something that's 2 or 3 pounds, drop 1 meter, that's how much energy you get across the battery. 12 pounds, 2 pounds? What weighs 2 pounds? If you had a textbook, kind of a medium-sized, smallish textbook, would be about 2 pounds. This thing is about 2 pounds. No, this is a little more. So if this is full of aluminum, if you have 2 of these, here's 2 pounds. This one is 2 pounds. Okay? Pass it around. How many of you would like me to lift that up 3 feet and drop it on your hand? Let it pass around. Would that feel good? It would hurt bad. And this is why you don't mess with car batteries, especially if you have wet fingers. Because it will hurt bad. That kind of energy going through your heart, if you touch both posts on them, your fingers are wet. When your fingers are wet, 12 volts can go right through your body. Okay? Because it creates a conduction, it creates conduction through your skin. You put that, it's like dropping this on your heart at 1 meter. It will stop your heart. Okay? It will crush your heart. Bad news. It hurts. Have you ever been shocked by something pretty extreme? Does it feel like somebody hit you with a hammer? Right? Like a bulky hammer, right? Probably the worst one I ever had was 10,000 volts I got 10,000 volts and some number of microamps from my right hand, no, my left hand to my leg or something like this. But it went down, it went through my arm and down my side, and my leg was touching the metal thing that was grounded. And it felt like somebody hit me with a ball peen hammer on my leg. It hurts. Same amount of energy. So that's what they're saying here. 12-volt motorcycle battery. That's what that means. It's got that kind of energy to move charge. So if it can move 5,000 coulombs of charge, now that matters with batteries, because batteries can only move a certain amount of charge because they're a chemical thing. So the chemicals inside the battery determine how much charge they can move. So we have this 12-volt motorcycle battery. It can move 5,000 coulombs of charge, and we have a 12,000 car battery that can move 60,000 coulombs of charge. How much energy does each one of these deliver? Remember that potential difference or voltage is per unit charge. So it matters how much charge these things can move. That determines the amount of energy that they can do. We said 1 coulomb. Let's see what happens when we put in 5,000 coulombs. So remember that the equation is voltage equals change in potential energy over charge. So they've rearranged the equation so that change in potential equals charge times voltage. So they multiply the charge times the voltage, and they get 6 times 10 to the 4, which is 60,000 joules. Now, how many joules did we talk about? We said 12 joules with 1 coulomb. So what can a car battery really do to you if your hands are wet? A lot more, right? So a car battery, a motorcycle battery can crank a lot of amps, can crank a lot of current. And if your hands are wet, and that 12 volts can push that current into your body. Bad news. And for the car battery, 60,000 coulombs at 12 volts. Of course, we're talking about 720,000 joules, a lot of energy. What does the car battery need that energy for? What does it use it for? Nope. Battery doesn't power your car, believe it or not. Doesn't power your car electrically either. Battery doesn't do it. Believe it or not. The battery is there for one thing only. To start the car. That's all the battery does. And that takes a lot of work because there's a lot of friction, there's a lot of weight, there's a lot of things that have to happen as you turn the starter motor. The starter motor is an extremely powerful motor inside the car that has to turn the crankshaft, it has to compress the pistons, it has to create spark inside well, it has to turn the alternator so you can create spark in the spark plugs, turning well, depending on what kind of engine you have, but anyway, it has to create spark in the spark plugs. It has to actually, it has to move cold oil in the wintertime. It has to do all these things. It's a lot of work that has to be done. For a car, it's about 700,000 joules of work that has to be done just to start the dumb car. Okay? And usually batteries are overpowered so that if they're a little bit low in voltage, they'll still start your car. Or if it's cold outside, that affects things. It affects the battery's performance. It still starts your car. But that's pretty much what it does. Once the car has started, then it's self-perpetuating. The spark plugs are run off of the turning of the engine because the turning of the engine turns the generator sparks the spark plugs, which fires into the cylinders, and the cylinders keep pushing the crankshaft around. So it just keeps going on its own. You can disconnect the battery and you're good. Everything will run off of the generator, off of your alternator and your generator, and you're good to go. In fact, old-fashioned cars, did they use a battery? Back in the Ford Model A and Model T days, they didn't use a battery to start. They used a crank. You just cranked it by hand and got that engine moving, and everything worked just fine. Of course, they didn't have as much electronics as we did, but they didn't need as much. Yes?
So then how can you realize
Because when the car is not turning, the generators aren't moving, and the lights are running off the battery. So when your car is not started, everything is run off the battery. It is connected so that you can turn on, see things and do things in the car. And that's why most new cars have an automatic shut-off switch. so that if the car is not turning over and your lights are on, it just shuts them off after some trip.
The electric cars that are made right now, and like the Teslas, for example, that use like gas stations, but not gas stations, more like
Yeah, power stations. Yeah. Yep.
to charge the car.
Yep.
Doesn't the battery or batteries make the whole car work?
That's correct. So, it's somewhat correct. In the electric cars, like there's the Chevy Volt and there's a list of them. The Tesla being probably the most famous one. They have huge batteries or banks of many batteries. In the case of the Chevy Volt, they have one big battery. In the case of the Tesla, they have a bunch of little batteries. But in any case, what they do is they run the entire car off of batteries, but they also have generators in the car. The generators are in the brakes, for example. When the car brakes, it has two kinds of, maybe three kinds of generators that recharge the battery as it's braking, and it only recharges a little bit, but it's helpful. I don't know if there are any others. There probably are some others. There's probably some heat sinks around the motor that takes the heat and turns that into electricity, because that can be done. It's not hard to turn heat into electricity. So, there are certainly cars that use the batteries while they're driving, and those are electric cars and hybrids as well. Hybrids also use their batteries while they're driving, but they have a motor that charges the battery also. So you turn on my mom's or my mother-in-law's Prius, and it doesn't make a sound, because all it does is connect the battery. But if you leave it there and don't start driving at all, just leave it sitting there on, eventually the motor will kick in to charge the battery, to make sure that it's charged. So, and the Prius is nice because you don't have to have a charging station, you just have to fill it with gas every month. It doesn't take much gas. Right? So, but they're also very complicated, so they're really expensive to fix. So here's another example. We have a 12-volt car battery running a single 30-watt headlight. Now, what are watts? Remember last semester we learned that watts are joules per second. So watts are the amount of energy that you're using in time, kind of like a velocity for energy. And so if we have 30 watts, you're using 30 joules per second. Right? So how long, or how many electrons are going to pass through each second? Well, let's take a look at some of the equations and see if we can figure this out. One of our equations says that the change in potential energy is equal to, it says that voltage is equal to change in potential energy over Q, so we can rearrange that to say that change in potential energy equals Q times delta V. And we can also rearrange it to say that Q equals delta change in potential energy over the potential difference, delta V. So we actually know both of these things. How much energy is it, how much change in energy are we going to experience if we go through a 30-watt headlight? Well, it's going to be 30 joules every second. There's going to be 30 joules of energy change every second. So that's our 30 joules. So we put in 30 joules. We put in our 12 volts, and we get a negative 2.5 coulombs. And that's going to be negative 2.5 coulombs per second. And how many electrons is that? Well, there's 2.5 coulombs, and there's 1.6 times 10 to the minus 19 coulombs per electron. Both of them with negatives and negatives and negative charge. And then you find that it's 1.56 times 10 to the 19 electrons passing through that circuit every second. Now, this is where we can actually kind of understand a little bit of where what's it mean? Benjamin Franklin. That's the amount of charge that an electron has. It is an absolute smallest number of charge. So we call it a quantum. That's the smallest amount of charge that exists. That is the quantum for charge. That is the amount that charge comes in. It only comes in that much. Does it come in half those amounts or anything? It's just that much. It comes in electron and proton. If you start talking about quarks have fractional charges, but they can't exist on their own. And when quarks are combined to make something that always make a charge that's either this charge or positive this charge or zero charge. It's the only kinds of charge you can have for a particle, for a quantum particle. But anyway, this actually gives us a little bit of an idea of where Benjamin Franklin messed up. Because Benjamin Franklin, when he was doing his kite experiments and his other experiments with charge, he thought that the charge that was electricity, that carried the electricity through a circuit or through the kite string or whatever, he thought it was the positive charge. And so that's why he gave the electron the negative number. He wanted the positive charge to carry the charge because that made the math nice and easy. But he chose the wrong one. We had 50-50 chance. And he chose the wrong one. It turns out that it's the electron, or the charge that was on his rod of whatever that stuff is, that fossilized tree sap. It was the charge that was on that was actually the charge that moves back and forth between things, and the positive charge stays still. So we're stuck with this negative sign that kind of kicks around a lot when we're dealing with electricity and magnetism, unfortunately. Okay, so now we have defined potential difference, which is this potential energy per charge, voltage. Remember that voltage is not potential energy. It's the amount of potential energy per charge. So it's kind of like it's almost like a potential energy density, you might think of it, or something like that. But it's certainly not potential energy exactly. It's not. It doesn't have the same units. Q is for charge. So no, it's just whatever charge you have in that particular situation. It could be 5 coulombs, it could be 1 electron at negative 1.6 times 10 to the minus 19 coulombs. Just depends on what charge you have going in the situation you're dealing with. That's just the charge. Usually when we call it little q, that means a charge that's like a free charge that's moving around or doing something in the problem. And when we have a big Q, usually that means some object that is charged up creating a field. So we use little q and big Q both in different situations for charge. Okay, so now a new way to think about this. When you're dealing with small particles like electrons and protons, it's kind of hard to talk about how many joules of energy they're going to have because even a charge that's moving very, very quickly can have a very small amount of energy because it's so small, because its mass is so small. So we try to change it to make these energies correspond to the potentials. So we're going to use a new unit for energy, and the unit is actually related to this energy equation where we have either potential energy equals QV or kinetic energy equals QV, because it works either way. It's just energy is equal to Q times potential. And what we do is when we're dealing with these small particles, we actually are going to use this Q times V as our energy unit. And we're going to say that the Q is going to be equal to 1.6, or the elementary charge, 1.6 times 10 to the minus 19. And then the voltage will be equal to whatever the voltage is. And we're going to call this unit electron volts. So let's say that I'm doing an experiment where I'm accelerating helium ions. So the helium ion has 2 protons and 2 neutrons in it, right? And there's no electrons on it. It's an ion. It's been ionized, have both electrons removed. And I'm putting it inside of an accelerator that has a positive plate on one side and a negative plate on the other, the hole. I'm going to shoot it out this thing. This happens to be an experiment that was done by a lot of scientists. And it's similar to this one, except this one has an electron in it. Let's say I'm going to do this one with my helium ion, and I'm shooting these particles out. I'm ionizing helium, putting them in the tank, and shooting out. Well, if the particles go completely across this potential, if they go from one plate to the other, then they have gained all of that potential energy in kinetic energy. All of that potential has turned into kinetic energy for each charge that comes out. And I could go ahead and calculate the actual potential energy of each charge by plugging in the charge value, which is 1.6 times 10 to the minus 19 times 2, because there's 2 protons, and then multiply by that voltage. Or I could just say, well, I've got 100 volts, or 5,000 volts, or 20,000 volts from one plate to the other, and I'm just going to call it 20,000 electron volts. Because that just tells me that this particle went through 20,000 volts potential. And so I'm going to say that its energy is 20,000 electrons. Because 20,000 volts is not an energy, but if you multiply it by the charging electron, it is an energy. And the reason that we do this is just to make it easier to talk about the energy. So a 5,000 volt can produce a 5,000 electron volt energy in electrons or in protons, depending on which way it goes. If you're using other particles, you still use that same unit. And this is what particle physicists, this is one of the units that particle physicists use quite a bit. Now, if you're told an energy, if you're given an energy in electron volts, you're going to have to convert it at some point. Well, you might have to convert it at some point to use it in other equations. You might want to use it in joules. So if it's electron volts, what you do is you divide by the electron to get your, let's see, is this right? You're going to, do they even give it to you? They really don't. But anyway, what you're going to want to do is you're going to want to essentially know how many charges that you have. In the math, what you would do is you would multiply by how much charge you do have. In our case, we have 2 protons, so it ends up being 3.2 times 10 to the minus 19 coulombs of charge. And then we would divide by the electron charge, because the electron charge is linear. So you take your electron volts, and you'd multiply by your charge and divide by the charge of an electron. And then you would know your energy in joules. They don't really do that here, but it's not that hard to figure out, I guess. But in the end, it's just multiplying electron volts times the number of charges. It's multiplying your electron volts times the number of charges that you've got. Okay, so conservation of energy. Turns out conservation of energy is the same. In fact, it's even better for charged particles. Charged particles tend to be quite small, so they tend to not be affected by things like friction very much. And so energy is conserved quite well because there's not a lot of outside influence. It's not to say that there is never any outside influence, it's just these very, very tiny particles are often pretty independent of them. But the kinetic energy plus the potential energy is still going to be a constant as long as there are no outside influences changing things, so that you can say the kinetic energy initial plus potential energy initial equals the finals added together just like before. But remember that potential energy is different in electrical charges. Instead of having mgh, you're going to have Q times V for your potential energy. Whatever charge it is times the voltage that it experiences. Right? And then then the kinetic energy stays the same. It's the mass of your charge particle, times velocity squared over 2, the 1/2 mv squared. You can rearrange this equation and actually solve for the velocity of the particles and travel through a potential, so that you get the square root of 2 times the charge times the voltage divided by the mass of the particle. And for an electron, in this case, at an electron that's going through a voltage of 100 volts, it turns out. They calculate it using the charge of the electron, and it's a negative 100 volt, or negative 100 joules per coulomb. And then divide by the mass of the electron, you get 5.93 times 10 to the 6 meters per second. How fast is that? almost 6 million meters per second. Right? It's pretty fast. So if you have 100 volts, which is what we have in our walls, essentially, you have 100 volts in the walls, and your electrons are going through this potential of 100 volts, they're going to get to be about 600 million meters, or 6 million meters per second. Right? How many of you have heard the rumor that electrons travel the speed of light through circuits? Anybody ever heard that before? It's common. It's a common misconception. What is the speed of light?
Like faster
3 times 10 to the 8 meters per second. And we're talking 6 times 10 to the 6 meters per second. How close are those two numbers to each other? How much smaller is this one? 100 times smaller. So it's going 1/100th the speed of light. Right? That's still pretty fast. It's extremely fast. And as you get higher and higher voltages, you can get closer and closer to the speed of light. But once you get to a certain point, you actually have to consider relativity. The electrons start to behave very differently than they would normally behave. But in normal circuits, normal kind of situations that we deal with every day, they're a good 100 times slower than the speed of light. Still moving pretty quick. Okay, that took us forever. Section 1, the long one. So, electric potential in a uniform electric field. So far in this chapter, we've talked about potential energy of a charge as it moves through a distance in a field. And then we talked about the idea of the potential. But if it's if we're in an electric field and we're not just between two charged plates or something, how are we going to figure that out? So we're going to start in a uniform electric field. Remember, the uniform field is one that has parallel lines and they're straight, right? They're not curving or anything. And so the electric field is pretty much the same everywhere. Notice that we're still using plates. That is fine because you can create a uniform electric field between two plates pretty well, except near the edges. And near the edges you get this little bending effect that we call edge effects. But the electric field in here is actually very uniform and you can calculate it. We don't have the skills to calculate it quite yet, but we're going to calculate it using a slightly different method. And that is the work that is done on the charge. Well, if a charge goes from 0 to some velocity, and something did some work on it to do that, wouldn't the work done on the charge equal the change in kinetic energy according to our work energy theorem? It would. So we know the energy it's going to get is going to be equal to the charge that's in the field, times the potential difference. And if we know the potential difference between these plates, let's say that we know that it's 100 volts between these plates, then we can just take that charge, Q, and multiply by the 100 volts, and that will give us how much work was done. Right? And we're going to define the electric field, we've already defined the electric field actually, as the amount of work divided by the distance. How have we already defined that? Well, because we defined field as force divided by charge, right? And work is equal to force times distance. So if we divide potential by distance, we're going to get field. It may not be completely obvious how that works, but it's true. Anyway, this ends up being the value for the electric field if we have the voltage and the distance that the charge traveled. Here's some of that math. This work equaling the charge times the voltage, which is the potential energy, right? And then the potential energy equaling charge times electric field times distance, which gives us, when you multiply the electric field times distance, you're getting work because it's Q times E is the force, Q times E times distance is work times distance, which is force, force times distance. So it becomes force times distance equals work, so both of these equal to work. And then you can solve for the electric field equals voltage over distance. Well, if that's the case, electric field equals voltage over distance, we can take our previous equation for electric field and calculate and make an equation for voltage. Remember, what was our previous equation for electric field? Electric field is equal to the charge that causes the electric field times K over distance squared, right? Well, we're going to get rid of one of these distances because potential equals E times distance, or instead of D, we're going to use R because we used R in this one. And that ends up being E times R. So voltage is going to equal K times Q over not R, but R squared. Not R squared, but R. So now we have an equation for the potential near a charge Q. But we said potential has to have a 0 point, didn't we? When we do this problem, we're assuming that moving the charge as far away as possible will take an infinite amount of work. We're assuming that if we're starting at one point, and if we move it as far away from possible, that will take an infinite amount of work, which means as far away as possible, or at the infinity point away from where we started, is the 0 point. So that's kind of weird, but we're assuming in this case that infinity is where our potential is 0, and our kinetic energy is at maximum. So anyway, here's an example where we'll use this a little bit. The equation that we're dealing with now is voltage between points A and B is equal to the electric field times the distance between A and B. Pretty simple. So we have dry air will support a maximum electric field of 3 times 10 to the 6 volts per meter. What that means is that air is made of particles, right? It's made of mostly of nitrogen, but these particles have charges on them. And as you increase the electric field, these charges get stretched apart. So the nitrogen and its electrons, the nitrogen nucleus and its electrons, get stretched apart. Eventually, you get to a point where the electric field is so strong that it rips the electrons off of the nucleus of the nitrogen, so that you have charged particles in the sky. When you have charged particles in the sky, the sky cannot support that electric field anymore, and it turns the air into a wire because you have charges in the air. What happens when that occurs outside? You get lightning, right? When you get charge moving through the sky now, like a wire, electricity moving through the sky like a wire, like it would through a wire, that's what we call lightning, and that's what's going on here. We've got dry air will support this maximum electric field strength of 3 times 10 to the 6 volts per meter. So if you have a meter distance between your two charge sources, and that you can get 3 million volts between those two charges in dry air before it will strike lightning. Okay. So, what happens if we have two parallel conducting plates that are separated by 2.5 centimeters of dry air? Right? So the maximum electric field, we've been given a distance. We know the maximum electric field. We want to know what the potential. I guess we're calculating the potential at this point. So we have 0.025 meters, 2.5 centimeters. That's our distance. Here's our maximum voltage, maximum electric field that can be created there. What voltage are we going to get? We're going to end up with 7.5 times 10 to the 4 volts, which is 75 kilovolts. So between two plates like that, if you create the maximum electric field, you'll get a voltage of 7.5 times 10 to the 4 volts across those plates before they break down. Okay. 75 kilovolts. And that's exactly what happens on the Earth. On the Earth, what you've got is you've got the ground at the ground, and you've got clouds overhead that are getting charged up. And as the clouds get charged up with whatever charge they're getting charged up with, I believe they get charged with a positive charge on the bottom side of the clouds. You get this positive charge on the bottom side of the clouds that's getting really, really strong. Well, it starts attracting electrons in the ground to underneath that point, so that you get a big negative charge on the ground. And as you build up this negative and positive charge, negative on the ground, positive in the cloud, eventually you build up an electric field that is strong enough to rip apart the atoms in the sky and create a wire, so to speak, in the air, and then electricity travels. Turns out the current travels from the cloud. Let's see. No, I think the cloud gets negative. So the cloud gets negative, the electrons travel from the cloud to the ground. So let's take a look at an example with an electron gun using this idea. We have two parallel plates. We've already talked about this. This is an accelerator. Two parallel plates, and they're separated by 4 centimeters, and these parallel plates will give electrons 25 kilo electron volts of energy. So we're going to have to convert from kilo electron volts. And we want to know what is the electric field strength between the plates, and what force would this field exert on a piece of plastic that has a 0.5 microcoulomb charge that gets between the plates. So first of all, electric field. The electric field is the voltage between A and B over D. The voltage is 25 kilovolts. Because that's the reason we use the kilo electron volts, because we know how much energy is given these particles. We also know, in kilo electron volts, we also know what is the voltage between the plates. You take that 25 kilo electron volts, you divide out the electron, and you're left with 25 kilovolts. And that's how much energy there is between the plates. How much potential there is between the plates. So we have 25 kilovolts of potential between the plates, and we divide by the distance between them, 0.04 meters, or 4 centimeters, and we get 6.25 times 10 to the 5th volts per meter. That's how much electric field there is. And to get force from electric field, you just multiply by the charge you're going to put in there. This little piece of plastic has a charge of 0.5 times 10 to the minus 6 coulombs. We multiply that by our field, 6.25 times 10 to the 5th volts per meter, and we get a force of 0.313 newtons.
I'm still a bit confused why we didn't convert the kilovolts to why do we need
To convert the kilovolts to volts,
yeah.
we did, but they didn't show it. Okay? And that's something that this book will do after a while. It'll stop doing every single step. But what they did is they took the 25 kilovolts and they called it 25 times 3, right? 25 times 3 volts. Then they divided by 0.04, and they ended up with the 10 to the 5th. So they did do it, they just didn't do it explicitly. Good catch though, because the fact that you caught that means that you knew it had to be done. That's good. Don't forget that those conversions do have to be done. So what is our relationship between voltage and electric field, or potential difference in electric field? It really has to do with distance. And again, they're using a different thing for distance here. Instead of R or D, they're using S. And why they're doing this, I think. But essentially, if you take your potential and you go through a particular distance that has that potential between those 2 points, and then you divide that potential by that distance, then you will get the electric field. Now, there is a negative sign in there. The negative sign comes from our friend Benjamin Franklin, but that's okay. But here they explain it as, the minus sign tells us that electric field points in the direction of decreasing potential. And that's as good an explanation as well. Just as good an explanation. But it also comes out in the math if you do the calculus part of it. So now let's do this equation. We already know the electric field from a point charge. And if electric field is related to voltage by dividing by distance, then we can say that the potential near a point charge is equal to kq over r if the 0 point for the potential is at infinity, an infinite distance away from that point charge. So it's pretty simple stuff. And to get back to the electric field, we just divide our potential by the distance and we get electric field. So here we have static electricity, right? Static electricity charges are usually, when you're walking around on carpet or something, they're usually about nanocoulombs or microcoulombs, not much bigger than that. We want to know what is the voltage 5 centimeters away from the center of a 1 centimeter diameter metal sphere that has a static charge on it that's kind of normal, -3 times or negative 3 nanocoulombs, which is negative 3 times 10 to the minus 9 coulombs. Well, we're just going to use this equation. Our Q is that charge, negative 3 nanocoulombs. And the K is the same. The distance is chosen for us, 5 centimeters away. Plug all those numbers in. We get negative 539 volts. Do you believe that? Walking along on the carpet for a fairly long time, and then you touch somebody, 500 volts. I believe it. You can get a pretty good shock from that, right? And it can hurt really bad on your finger if it's a single finger. If all that energy goes through one spot and you get a lot of charge built up. Yeah, you can do that. So yeah, why not? Now here is an example of building up a lot of charge, and it's using that device back there. This device is pretty simple actually. There's a motor in the bottom that turns a wheel, and connected to this wheel is this rubber belt, and there's another wheel at the top. At the bottom here, close to this wheel, there's a thing that they call a comb, and they don't really show the comb. They should. But the comb is connected to, the comb is really close to the belt, and it just looks like a little metal comb. It's really close to the belt, and it's connected to ground so that it can get electrons from ground. And what it does is, as this belt comes past this metal comb, the electron affinity, the electrons want to be on the belt more than they want to be on the comb, so they jump from the comb to the belt. The electrons get pulled up here. I believe the electrons go to the top on these things. But anyway, the electrons get pulled up to the top, and there's another comb that is connected to this big sphere at the top. And that comb takes the electrons off the belt, it turns out. So you build this huge amount of charge on that top sphere as that belt goes around and around and around and around. Now, the amount of charge that you can put up there depends on a few things. It depends on the height of the thing, because the higher it gets from ground, the harder it is for you to build up that electric field strong enough for it to strike electricity to the ground, for it to drain off that charge. So you can build more and more charge. But also the size of the ball on the top matters, because a bigger ball can hold more charge. It's like a bigger room can hold more people, right? So those two things determine how big of a charge you can build up on this and how much voltage. Well, we've got some of those ideas right in this equation. Voltage is the thing that we're going to build up, is the amount of charge that we can put up there. That's related to the size of that thing, right? But the radius is also related to that size, so that radius is up there as well. In this case, we're going to rearrange the equation to calculate the amount of charge we put up, and the voltage that it can withstand depends on that distance, depends on the height, so that voltage is there. So now we have something that's dependent on distance, and they've told us that number, how much voltage builds up. And then they've also told us the radius of the sphere, so that'll tell us how much it can hold. We're going to divide by K, and we get this amount of charge, 1.39 microcoulombs, it turns out, for 100,000 volts. It's not that much charge. 100,000 volts with that tiny bit of charge, microcoulombs of charge. And that's why getting shocked by one of these classroom models is not that big a deal, because there's just not that much charge going into you. Right? If you're talking about a really big one that's very tall and has a huge sphere on it, you can build up more and more charge, and that charge can come at you with a lot of energy, and then it can be really, really bad. It'll hurt if you get shocked by that, but it won't stop your heart or anything. It's just not enough current, not enough charge. Okay. So, I'm talking about two different things when it comes to electricity that have to do with the strength of what charges can do. We've talked about what kind of forces charges can exert, and we used field lines to do that. The closer together the field lines, the stronger the force, right? The direction of the field lines told you which way the force was going. But we've also talked about potential. The potential difference that a charge causes, that a charge creates, can accelerate charges, which is like a force, right? It's a force. It can change their kinetic energy, right? And so the potential difference is also one of these things that we can talk about. But the interesting thing is that these two things, the potential difference and the electric field, are kind of parallel to each other if you make a graphical representation of it. So here is a positive charge with its blue field lines pointing out like the spokes of a wheel. And these green lines are actually places where the electrical potential is equal. So if I walk along this green line right here, my potential energy will always be the same if I have some charge. If I'm an electron, I can sit right here on this line and I can actually go around and around and around, and I won't lose or gain any energy. I'll just sit in that little sphere at that particular distance away, because the potential energy that I have is always the same. The kinetic energy that I have will always be the same. So I'm not changing energy. No force is acting on me. If I am down on this one, and if I'm a positive charge, I will actually have more potential energy. In other words, getting closer to a positive charge gives you a higher potential. Closer and closer to a positive charge, you have a higher and higher potential. But if it's just a single point charge, then this circle that is concentric with that point charge is what we call an equipotential line. Everywhere on that, the charge can go without being forced to go there. It can just hang out there. When people were first studying atoms, they thought that this is how electrons behaved, how they kind of were held in on the atom. You had these protons that were pulling the electrons in, but they were orbiting in these equipotential planes, these equipotential spheres. Turns out that cannot be the case due to some things that Einstein discovered. And when Einstein discovered those things, they threw the entire world of chemistry and physics on its head. But later on, physicists were able to come up with some explanations that accounted for it. But these are called equipotential lines, and equipotential lines are always, always, always perpendicular to field lines. Always. And they always exist at places where the electric field is the same. So that's where they go. So this particular line, if you go all the way around, the electric field is the same everywhere. The electric potential is also the same. And this one, the electric field is different than it was down here, but it's the same all along this one. So these equipotential lines are like places, show you places where the potential doesn't change. The potential is the same on those lines. You'll notice that as you get closer and closer to a charge, the potential lines are closer together. As you get further away, they get further apart. So when potential lines are closer together, the electric field is stronger. And when potential lines are closer together, you have a higher electric potential. When they're further apart, you have a lower electric potential, and you have weaker electric fields. Here is an example of some electric potential lines in a dipole, electric dipole. So we have a negative charge and a positive charge. The field lines go from one charge to the other right in between here. And you can see that the electric potentials are shifted now. They're pushed towards the charges. And right in the middle, there's an electric potential line right there. So that potential is the same right on that line. What happens if I put a charge on that line? What will happen to that charge? It'll just sit there. Because the potential is the same everywhere along there. It could travel up, it could travel down, but it can't go any closer to either one of these charges. So a charge that goes right between these two things could travel right between there and never feel the electric field from either of these charges. This is where the electric field, let's see, you still feel the electric field, that's incorrect. But the potential difference is there's no potential change there.
Wait, will it go down or up, or will it?
It actually will turn because it doesn't follow this line, it follows these lines. Right? But what I said about a charge being on the potential line is only true if you have the right kind of energy. So I made that mistake earlier with the other picture. So your charge can move around on this line without changing its potential energy, but it has to have a kinetic energy to it to do that. So it has to be orbiting, in other words. The problem with that is that it doesn't work out so well when it's a charge. So I made a mistake with that. It can move, it can stay along that line, but it has to have the right kinetic energy to cancel the correct kinetic energy. So the kinetic energy plus the potential energy is 0. So here's another one with 2 negative charges. Right? This one, for sure, if you put a charge right here in the middle, will not go anywhere because it essentially has this potential in the middle of nothing. I mean, there are no equipotential lines in there. There's nothing going on in there. And the electric fields are canceling each other out in there. The important things to remember with equipotential lines, because you will use this both in your lab and in your homework. Anywhere you're on, anytime you're on an equipotential line, and you're following it around and you're staying on that same line, you always have the same potential, same voltage, in other words. It's always the same voltage on that line. So you have the same potential to be accelerated or whatever else. But those potential lines are always perpendicular to field lines. Okay? So if you have the potential lines, you can draw the field lines by drawing perpendicular lines between positive charges and negative charges that are always perpendicular to those potential lines that you've been given. If you have the electric field lines, you can always draw the potential lines. Because potential lines are always going to be perpendicular to electric field lines. And they're always going to cross electric fields where the fields are equidistant apart. The field lines are equidistant apart. So those are the things to remember about the potential lines and field lines and their relationships. We will use that quite a bit. And here you can see examples of that. Here's an example of the equipotential lines in a uniform field. Remember, uniform field means it's the same everywhere. And that means that the potential lines are going to be not only parallel to each other, which they never cross each other, just like field lines don't, but they're going to be equidistant. If you had more of these lines in here, if you decided to draw these instead of 25 apart, you drew them 5 apart, they would always be equal distance. So that no matter where you moved in the field, you're going to feel the same acceleration because the field is the same. The forces are the same. They actually fixed the links. Let's see if it works. Apparently it doesn't work. All right, that's fine. Let's see, how many sections do we have here? Capacitors, energy stored in capacitors. I think I actually want to save these last 3 for next time because it's all about capacitors. It'll be our first electrical device that we talk about. We've already talked about it a little bit without telling you. But let's go ahead and save 19.5 to 19.7 for Wednesday. And, excuse me, we will go forward with our lab tomorrow and everything else. So, the homework for this chapter I have not posted yet on Expert TA, but I will go and I will do that right now and choose the appropriate homework problems. I will be here until, what time is it now? 10:20. I will be here until probably about 1 o'clock today. So you've got almost 3 hours, minus the time that I'm going to use to put together this homework assignment really quick right now. So I'm going to go work on that homework. Maybe 15 to 30 minutes, I'll be available for homework questions. So get started on working on things that you have questions about. If you still have questions on the last homework, and then I can come and help you out. Make sure not to take those magnets on your hat with you. I use those a lot around here. I have like 100 of them. But okay. So anyway, I'm going to go work on that homework assignment.
Hey, quick question about the electric field in the atmosphere. Is there kind of a certain limit before the voltage kind of breaks down the resistance? I mean, is it kind
Yeah.
of stuck at a certain limit before it just and
Yeah,
light-
for dry
lightning-
air, it's about that million volts.
And lightning is just the drain where it cuts off and electric.
Yeah,
field.
it's just when it has created this line of ionized gas between the cloud and the ground.
Okay, I
And
just
so the ionized gas behaves like a wire.
okay.
Electricity travels down. Oh, I need to stop my video here really quick. Where's my video? Okay. Stop recording.